Hi, my name is Rajiv Kumar, a research scholar from Indian Institute of Technology, Bombay. I will present our paper, the MIS Checkdam Dataset for Object Detection and Instance Segmentation Task, co-authored by Chintan Tundia, Professor Om Damani, and Professor G. Shivakumar. I would briefly introduce the motivation for creating a novel dataset called the Minor Irrigation Structures Checkdam Dataset, mention its characteristics, compare it to other datasets and the challenges in object detection in aerial images, followed by the benchmark results in object detection and instance segmentation on our novel dataset. With the recent improvements in imaging technologies of the satellite sensors, large volumes of spatial resolution data are available, resulting in the application of object detection in remote sensing for identifying objects from satellite, aerial, and SAR imagery. This availability has led to various applications such as target identification, building detection, road detection, etc. In many developing nations, various man-made agricultural and irrigation structures are used for farming, like wells, farm ponds, and check dams. These irrigation structures have a short construction period with low investment requirement. Check dams are artificial irrigation structures built across water bodies that provide irrigation facilities to nearby and surrounding area up to 2,000 hectares. In this paper, we introduce a new dataset of check dams from satellite images for building an automated system for detecting and mapping of check dams. In India, minor irrigation census is conducted every 5 years. This helps in rural planning, formulating various policies, and in reserving and allocating funds for agricultural development. The data is collected from village level workers and administrators by ground survey or land record surveys of government and private scheme owners. The issues in census process are remotely located villages, unavailability of village records and staff, which makes the census process lengthy, error prone, and costly. In comparison to datasets like COCO, ELVIS, and ImageNet, satellite imagery have small, densely clustered objects of interest with a small spatial extent. There are several datasets in remote sensing that use images from multiple sources like airplane, drone, and satellites. Some of these datasets focus on static objects like pools, playgrounds, buildings, stadiums, etc., while some of these datasets have non-static classes like vehicles of different types, cars, ships, airplanes. Also, aerial image datasets have objects of different orientation ranging between 0 and 360 degrees. Here, we summarize the classes and object instances of various related optical satellite image datasets. While some datasets have very high resolution images, some datasets have instances ranging from few tens to a few tens of thousands. The most similar dataset to ours in terms of type, classes, and object instances are other minor irrigation structures like farm ponds and wells. The wells dataset has 1614 instances over 1011 images, and the farm ponds dataset has 4 classes in 715 instances over 1018 images. Here I will mention briefly the details of our MIS checkdam dataset. Our dataset has 1082 instances of checkdam across 1037 images of 640 x 640 pixel dimensions. Object instances come from two categories. We have 562 instances of wall-based checkdams and 520 instances of gate-based checkdams. All objects were captured at zoom level 19 using Google Maps API, and the annotations were performed by domain experts. In comparison to dense object datasets such as cars in aerial images, Our dataset has images consisting of sparsely located objects. The satellite images collected from Google Maps, span seasons and collection times. The imaging conditions also vary due to the presence of air pollution, clouds, weather condition, and different image sensor types, which leads to blurry images or image tint. Moreover, there are wide variations in the surrounding vegetation even under a small geographical area. An object captured from one angle may cast a shadow and appear differently based on the time of image capture. Also, the presence of trees and surrounding vegetation may occlude the check dam. Moreover, a check dam and its surrounding appearances vary depending upon the water level, seasonal rains, and the irrigation purposes. Check dams are subject to size variations due to their surrounding environments, and the instances are geographically far apart from each other. Unlike other dataset classes, our dataset has object instances with large intra-class diversity and inter-class similarity. Since a check dam is built across a river or water body, it is easy for a human with domain knowledge to identify and distinguish the structure between a check dam and a bridge. However, the width of a water body varies along its trajectory, giving rise to large variation in check dam size in comparison to objects like cars or planes in other aerial image datasets. In terms of spatial resolution, Google Map API uses zoom levels ranging from 1 to 22 that correspond to image level spatial resolution. However, most objects of interest are available and identifiable at zoom levels of 17, 18, and 19. All checkdam instances in our dataset were captured at zoom level 19 for our dataset. These instances are visually similar to other objects like bridges, buildings, and huts in the aerial imagery that makes manual annotations difficult and the object detection and instance segmentation tasks tougher. Here we mention the details of the various metrics used for comparing the performances of object detection and instance segmentation methods. We use Pascal and Cocometric mainly, along with other MAP. We compare the performances of various object detection methods and the network architectures on our novel dataset. We have tried to include and benchmark using the latest transformer-based methods as well as one-stage and multi-stage object detection methods. We also compare the performances of various instance segmentation methods and the different network architectures on our novel dataset. Many of these instance segmentation methods double as object detection methods too. The qualitative results from detector RS on object detection task has been shown here. As visible, the test set includes object instances of both wall-based and gate-based check dams of various scales and collected from different geographies. Detector RS method using hybrid task cascade and switchable address convolution achieves 0.625 in the Cocometric and 0.749 on bbox MAP at 0.75. Detector RS method using cascade RCNN achieves 0.967 on bbox MAP at 0.5. The qualitative results from the best performing method hybrid task cascade has been shown here for instance segmentation. Swing transformer and HTC achieves 0.478 for segmentation MAP for levels 0.5 to 0.95 for instance segmentation. Eurolact achieves the best performance of 0.939 on segmentation MAP at 0.5. Prime sample attention achieves the best performance of 477 on segmentation MAP at 0.75. The results on our dataset can be used to assess and evaluate various object detection methods and their improvements over other methods. Most of these methods perform well on geographically versatile images as well as on different scales of checkdam instances. We perform both in object detection and instance segmentation tasks, and among all those methods, a swing transformer gives the best performance on cocometric at 0.6617 for object detection and 0.978 for B-box MAP at zero point 0.5. InstaBoost gives the best performance on B-box MAP with values of 0.722 at 0.75 IOU. Finally, the implementation of our various object detection and instance segmentation methods were performed using the detection framework. Many of the methods were trained in 1x, 2x, and 3x schedules, which corresponds to 12, 24, and 36 epochs. I like to conclude our work with the details about pre-trained models and datasets which are made publicly available. Our future work focuses on testing and adapting the trained model to various villages in India. Also, we have developed a 60K image classification dataset of the minor irrigation structures as a future work. We also plan to make MIS 3K dataset and object detection dataset for all the three MIS classes. Thank you.